Hi everyone! So, for those of you who don't know me, I am Miss Hu, your physics teacher. In this video, I'm going to go through with you how to solve the questions from this book, which is the Module and More Physics Form 4 book by Pelangi, focusing on the questions from the topic of Newton's universal law of gravitation. Now, if you haven't learned this topic yet, I highly suggest that you do, and you can go and watch my videos where I go through this particular topic, which I'm sharing on top here in terms of the link. But do learn this topic first before you try these questions. So in this video, we're going to go through the questions and solutions in English. By the way, this video is not meant to share questions with you, but rather to share the solutions to the questions in this book. So what you need to do is buy this book, try the questions on your own first, and then refer to this video for assistance if you need to figure out, or if you can't figure out how to do the solutions. So without further ado, let's begin. Now I'm only going to be working on selected questions, which are the questions which we need to learn how to solve. And by the way, I don't have the answers in hand, so I'm going to be working it out as I create this video. And of course, I've got my calculator with me. Just want to show you how to get started on solving these questions. So we're going to start with page 72, Contoh 2. Contoh is the example. And because it's an example, they've already given some prompts here. Basically, they show you how to get started on solving the question. That's why they've got this list over here. I'll go through what all these things are. So for question 1, you need to calculate the gravitational force between a buoy of 50 kilogram resting on Earth's surface. So they gave the mass of the buoy. They've also given the mass and the radius of the Earth, as well as the value of g, which is the gravitational constant. Now, over here, they've written the list here with M1, M2, R. This is really good practice if you're not sure how to get started on solving the questions, because it gives you an idea on what values you can use to substitute into the formula. So, looking at the question, you need to calculate the gravitational force. Change color to something that's easier to read. Right, we want to calculate the gravitational force, and of course, if you have learned this topic already, you know that to calculate the gravitational force, you need to use a formula of F equals G m1 m2 over r squared, where G is a gravitational constant, m1 and m2 are the masses of the objects which you are counting the force between. In this case, m1 and m2 would refer to the mass of the buoy and mass of the Earth. R would be the distance between the centers of both objects. In this case, if let's say this was Earth and let's say this is the buoy, you can of course argue that, the distance between the center of the buoy and the center of the Earth, it's not exactly the radius of the Earth. But because the height of the buoy from the Earth's surface is negligible, you can actually just ignore that and just take the distance between the center of the Earth and the center of the buoy to be equal as the radius of the Earth. And that's what they've done here. That's why they've taken R as the radius of the Earth. So you don't have to add in the extra height. It's negligible in terms of the difference. I'm just going to remove all this. Okay. So this example has already given us a formula. All you need to do is substitute the values in. So G, as we know, is 6.67 times 10 power negative 11. My apologies for the bad handwriting. I'm struggling with the tablet a little bit because it's not easy to write nicely on Jamboard with this. Okay, we'll take the buoy as the object 1 and Earth as object 2. And R, of course, is the radius of the Earth. Now, a common mistake that a lot of students make is to forget to square the value of R. So don't forget to square it. So we're going to use our calculator now to figure out the answer. Okay, and the value you should get is 490.67. Gravitational force unit is Newton. And that's your answer for question 1. Quite easy, right? Because it's just substitution. So you're going to learn to do the same substitution in question 2. Question 2 in this case, you need to calculate the gravitational force between the Earth and the Moon. So they've given us the distance between the Earth and Moon centers, the mass of the Earth, as well as mass of the Moon. Again, because you're counting the gravitational force, you need to use the formula of F equals gm1m2 over r squared. They've written here the values of m as me and mm. Me is the mass of Earth, and mm is the mass of the Moon. Now you can take the mass of the Earth as object 1. Sorry, you can take Earth as object 1, so this would be m1. And you can take Moon as object 2, so this will be m2. Even if you swap it around and make Moon the object 1 and Earth as object 2, it doesn't matter because basically you're counting the product of the masses. So that's why it really doesn't matter. So as long as you put the correct values of the masses in, you will be fine. So we're going to start with G first, and then we'll take mass of the Earth, and then mass of the Moon, and this time this R, of course, is the distance between the two centers, which we've already written very clearly here, right, between the Earth and Moon centers. So that's not a problem. We'll just take 3.8 times 10 power of 8. Don't forget to square it. A lot of students, sometimes they write the square, but they forget to put the square when punching the values into the calculator. So make sure that you don't forget to do that. 4, and just keying the values in. And we have the value of 2.03 times 10 to the power of 20 Newton. Just close the zeros up a little bit. And that's your answer for question 2. Very easy, right? Because it's a matter of substitution. So now let's get to page 73, Tugasan 1. So Tugasan 1, they don't give you the step-by-step on how to solve because this is now where you need to learn how to solve the questions. So in Chonto, it's an example. So this kind of example questions are supposed to be worked on in class. You know, with your teacher will work on these questions with you in class to show you how to get started. Tugasan 1 is something you need to attempt on your own. Now, whichever the case is, it's still not difficult because basically what's the question asking for? It's asking for the gravitational force. So looking at the question, you have a satellite orbiting Earth at a distance of 40 kilometers. They've given you the mass of the satellite as well as the mass of the Earth, and you need to calculate the gravitational force. So if you want to write out the list of values like shown in the Chonto questions, like what's M, what's R, it's actually really good practice to make sure that you've got the correct values for substitution. But let's say you're not sure, right? So what you can do in the future is to do this. Okay, you need to calculate gravitational force. So write out the formula first. I'm going to write it on this side to give some space for my list later. So I'm going to write it here as F equals G m1 m2 over r squared. And we know we need to solve F. So you need to make sure you have the value of G. It's not written in the question here, but normally it's given in a formula sheet. And we already know that G is 6.67 times 10 to the power negative 11. And what we need to do is we need to get M1, M2. So you can write it over here. Okay, I'm just going to switch colors, or rather I'm just going to highlight it for a bit. This is the mass of the satellite, and this is the mass of the Earth. And you can write that if you need to on this side. So for example, mass of the satellite would be 750 kilograms. And mass of the Earth, I'm going to write as M2 and then ME, 5.97 times 10 to the power 24 kilograms. So that's a value that you can substitute inside. Here, 750 and 5.97 times 10 to the power of 24. Now, for R, the satellite is orbiting at Earth at a distance of 40 kilometers. This value is 40 kilometers from the surface of Earth. You must remember that R is taken from the center of object 1 to center of object 2, which means that to calculate R, you need to take 40 kilometers plus the Earth's radius. So R should be 40 kilometers. Now remember that you need to bring them down to the same unit, which is meters. So that's 40 times 10 to the power of 3 to convert it to meters, plus 6.37 times 10 to the power of 6. Now, if you want to, you can just put these values and put it in the bottom, or you can solve the value of R first, which I will do for clarity. This gives us 6.374 times 10 to the power of 6 meters. So we're going to take this value and put it in the equation, and don't forget to square it. Whenever you're doing any calculations, don't round up while you're still substituting the values in. It's a good practice to round up or at the end after you've done all the calculation. But in between, don't round up. Don't like, oh, 6.374, I'll just write it 6.37. You're going to get the wrong answer. Okay, so now let's work it out. Like I said, if you wanted to just write all this, whoops, wrong pen. If you just wanted to, if you don't want to solve R first, you want to put all this value and put it in a bracket underneath, you can actually do that. That's not a problem. And don't forget to square the R, 6.374, 6 squared, and you should get 7.35 times 10 to the power of 3 Newton. And that's how you solve Tugasan 1, question 1. Let's look at question 2, which asks you to calculate the gravitational force between the sun and the earth. So in this case, another way you can do this, and this is my lazy way, as I call it. I'm just going to use a different color. So this is the mass of the sun. This is the mass of the earth. So sometimes what I do is, instead of writing out that list, I will actually just write it over here straight away. This is M1, and this is M2, and this is R. My tablet is not listening to me. All right, and you can straight away calculate the gravitational force from here. So using the formula of F equals G M1 M2 over R squared, we know that G is 6.67 times 10 to the power negative 11, mass of the sun as object 1, and mass of the earth as object 2. And we've got R as 1.5 times 10 to the power of 11. Don't forget to square it. And all you need to do is just use your calculator, work out the answer. And you should get 3.54 times 10 to the power of 22 Newton. Okay, let's go on to Contoh 3, page 74. So for this question, you need to calculate the gravitational acceleration of an object with mass 50 kilogram above the surface of the Earth. Okay, there's a little bit of a cutoff over there, but this is basically given the mass of the Earth and the radius of the Earth. So because if this is an example question, again, they've given us a list as well as a formula that you can use. So the formula to calculate the gravitational acceleration is G equals Gm over R squared, where G is the gravitational constant, M is the mass of Earth, and R is the radius of Earth. So that's why they've given this list over here, which is also taken from the question. To solve this question, it's just a matter of substitution. So we're just going to put in the values here, 6.67 times 10 to the power negative 11. Oops. Mass of the Earth, which is 5.97 times 10 to the power of 24. And R is 6.37 times 10 to the power of 6 squared. So I'm going to put the answer on this side, all right? So again, calculating it out, 6.67 negative 11, 5.97 times 10 to the power of 24. and we're going to square the value of r. And this will give us 9.81. Because this is acceleration, the unit is meters per second squared. Right, so now let's look at the next question, which is on page 75, Contoh 4. So for this question, you need to determine the gravitational acceleration at the location of a satellite. Where's the satellite? It's orbiting Earth at a great height, which in this case is 550 kilometers. So you can see over here, again, they've extracted the values from the question. So you've got mass of the Earth, r, which is the radius of the Earth, h, which is the height of the satellite, and you can see how they've written here as 10 power of 3 because they've converted kilometers to meters, and of course a value of g. So they show you how they obtain this value. Basically, they have derived this formula comparing the weight of the object to the gravitational force, which are the same. You cut, and you end up getting g equals gm over r squared. But because the satellite is orbiting at a greater height, the value of r, as you must recall, is between the center of the object and the center of this object. So you have to take the value of the distance as the radius of the Earth plus the height. That's why they've written it as r plus h. Okay, so in case you don't know what I'm talking about, it's because if this is Earth, I'm going to put it blue color, okay, because, and let's say this is a satellite. I'm just going to put one blob here, this satellite. So remember that the distance r has to be from the center of Earth to the satellite. So that's why you need to take this r distance as the radius of the Earth plus the height of the satellite. That's why they've written it here as r plus h. So just substituting the values inside, following the formula that's given here, 6.67 times 10 to the power of negative 11. M is the mass of Earth, which is 5.97 times 10 to the power of 24. And we add the radius of the Earth with the height of the satellite. And of course, all this has to be squared. 6.67, 5.97. Then we're going to add r together. You should get 8.32 meters per second squared. Or well, if you want to be more accurate, I'll put it to 3 decimal places, just because, why not, right? So it's 8.315. Because why not? Okay, and let's take a look at the next Contoh. So for this question, you are counting the centripetal force. So if you recall, centripetal force formula is F equals mv squared over r, which is given right here in the solution. Right, so to calculate centripetal force, okay, what was going on in the first place? So we have from diagram 2, okay, it's in the book, right? We have a 0.1 kilogram rubber stopper rotating with a radius of a circle of 40 centimeters, and you want to calculate the centripetal force when the rubber stopper is moving at a speed of 10 meters per second. So the mass of the stopper is 0.1 kilograms, radius is 40 cm, or as you know, you must convert it to meters, 0.4 meters, and its speed is 10 meters per second. So all you need to do when you want to calculate centripetal force is to substitute these values into the formula. So F is centripetal force, M is the mass of the object that's rotating. So that's the rubber stopper of 0.1 kilogram. V is the speed which the stopper is moving at. So it's 10, don't forget to square it. R is the radius of the circle, which is 0.4. So working it out. You should get a value of 400 meters. Looking at Contoh 6 now, you need to calculate the mass of the Sun. and they've given us all these values. So this formula, as you can see, is a modified formula from the centripetal force. Sorry, and it's already given. They've already given you the formula that you need to work with. So v is the linear speed. So how they got this value basically is because you know that the sun, oops, basically you know that the sun is in the center. Let me put that. Let's say this is the sun, and you know that the earth is rotating around the sun. Oops, I was trying to make it rotate. Rotating, right? So what happens is you gotta calculate. So what happens here is, okay, the formula actually was derived from comparing the centripetal force to the gravitational force, and this has been simplified for you. So all you need to do is just substitute in here. This formula is to calculate the linear speed of Earth. How they got this value is because we know that the Earth is orbiting the Sun, assuming that it's a circular orbit, right? The speed can be calculated by taking the circumference of that circular orbit divided by the time it takes to make one complete orbit. So that's why you need to get the radius of the Earth from the Sun, and that will be 2 pi r to calculate the circumference of that orbit. And t would be the time it takes to make one complete rotation around the Sun. That's how they get the value of v. So they put it over here, you need to just substitute it in. So 2 pi r, which is 1.5 times 10 power of 11, divided by the time in seconds, which they've already worked it out for us, 3,155,7600. Now, I didn't write the value of pi because you should use the value of pi from your calculator. So use the value of pi when you subbing the values in. This is 1.5 in case you can't see the dot. I nearly couldn't see it. And you should get 2.987 times 10 to the power of 4 meters per second. Then to work this out, you just need to substitute the values in. 1.5 times 10 to the power of 11 for the value of r. V is what we've just calculated, 2.987 times 10 to the power of 4 squared. And G is, of course, the standard 6.67 times 10 to the power of negative 11. So working this out, let me calculate that. Oh shoot, I pressed cancel instead. So let's try that again. This is 11. Goodness gracious. Alright, and the answer you should get is about 2 times 10 to the power of 30 kilograms, which is the mass of the Sun. Right. Oh, did I put that double? I did. So what I'm going to do is I'm just going to remove this. My bad. Delete. Oh, and yeah, this is supposed to be page 80, not page 79. Okay. And we now come to the final question, which I would like to cover in this video. So for this particular question in this book, for Tugasan 2, they want you to determine the mass of the Earth. And basically, they're showing you how to calculate the mass of the Earth. So given that you've got the mass of the object, and what they do is they compare the formula for the gravitational force with the weight, they work it out, and they simplify it down to this particular formula, where you can calculate the mass of the Earth by taking g r squared over g. So G is the gravitational acceleration, R is the radius of the Earth, and G, of course, is the gravitational constant. So here is just again a matter of substitution. So you would get, let's just use 9.8 because that is given in the question over here. 9.8, R is the radius, 6.37 times 10 to the power of 6 squared, and G is the gravitational constant, 6.67 times 10 to the power negative 11. And working it out, this is a square. Okay, that's number 2, by the way. I know the writing is terrible, but that's a 2. So 9.8 times 6.37. Don't forget to square it. And you'll get 5.96 times 10 to the power of 24 kilograms, which is the approximate mass of the Earth. And that's how you solve the questions in this topic in this module and more book. So if you liked this video and you found it helpful, please don't forget to click like and subscribe to get more free lessons and also solutions and exam strategies from your teacher, Miss Ho. Thanks for watching, and don't forget to share this video if you liked it. Also, yes, private lessons are also available. I'm putting the wrong way. Private lessons are also available if you'd like to engage me for help in improving your personal physics lessons. Okay, to improve yourself in terms of your physics. Happy studying!